In this video, we are going to state and prove the Bolzano-Weierstrass theorem, kind of a famous theorem. Anytime in real analysis, a theorem has a name, or two names in this case, it means it's a well-known theorem. So the Bolzano-Weierstrass theorem tells us that every bounded sequence of real numbers has a convergent subsequence. So your bounded sequence itself might be kind of jumping all over the place, but from that, you can extract a convergent subsequence. And that's it. So if a sequence of real numbers is bounded, it has a convergent subsequence. We are going to do two proofs, and that's it for this video. The first proof is so short and clean, it feels like cheating. So I'm going to do a longer, more technical proof, which is in many texts what's presented as the proof of this theorem. And again, it kind of comes down to how you choose to order your axioms and the results that you build off of those axioms in your study of real analysis. I brought in the monotone subsequence theorem kind of early because it gives us a really clean proof of the Cauchy criterion for the completeness of R, and it's about to give us a really clean proof of Bolzano-Weierstrass. So actually, let me pause for a second because I just said the key idea out loud. Take a moment to revisit the monotone subsequence theorem, and there's another monotone theorem, and see if you can come up with a proof of this statement. It should just be maybe about 3 sentences. I will write up a nice first sentence which introduces the name of the sequence. We'll call it A sub n. Let A sub n be a bounded, so BDD, bounded sequence of real numbers. All right, so now we have a name for the sequence. By the MST, monotone subsequence theorem, what does AN have? It has a monotone subsequence. That's true for any sequence of real numbers. And let me tack on to the sentence that this subsequence is also bounded because it is a subsequence of a bounded sequence. So any bound that applies to this sequence also applies to this one. Right. The adjectives monotone and bounded should always make your mind go to one place. When you are working with a monotone and bounded sequence of real numbers, the MCT applies. So that's the Monotone Convergence Theorem. So there exists a limit for the sequence because it is bounded and monotone. And that's actually it. We have shown the conclusion, the existence of a convergent subsequence. So we're done. And I could be done with this video. It would be a very short video for a very famous theorem. But there is another way to prove this, which is going to be much more involved. I think, however, it's a nice, elegant argument. It will involve kind of illustrating an idea, which I think is worth working through as students of real analysis. So while this has verified the Bolzano-Weierstrass theorem for us, the other proof is worth watching because the constructive ideas in the second proof are the kinds of tools which come up sometimes in real analysis. So it's good to work through that argument, even if we don't actually need to. This second proof of Bolzano-Weierstrass got a little big on the board, so I'm switching over to my computer. What we are going to do with our bounded sequence of real numbers is manually construct a subsequence which we will show is actually Cauchy and therefore convergent. To follow this proof, I think it's helpful to illustrate it as we do the proof. In the past, when I have graphed sequences, what I often did was create a two-dimensional plot where the horizontal axis was the sequential indices and the vertical axis was the sequential values. So we graphed sequences in the past as functions of the natural numbers. In this illustration, what I'm going to do is just plot the sequential values on the number line as they appear. So suppose I'm plotting here the first 3 sequential values, then the 4th one, then the 5th one. And what you'll notice as I drop these sequence terms on the number line is that they bounce around. We're just plotting the sequential values as they appear.
And a value can repeat in a sequence, so some of these dots are being mapped to more than once. At this point, we have plotted the first 25 terms of our starting sequence, whatever it is. You'll notice that dot in the middle corresponds to 5 of the first 25 sequential terms. I'm mentioning this because when you graph a sequence like this, and you map the sequential values onto the number line, it's not necessarily the case that your dots have a one-to-one relationship with terms in the sequence. For example, if you wanted to graph a constant sequence, you would have a single dot on the number line, but that single dot would correspond to infinitely many terms because it represents every single term in an infinite sequence. Okay, so imagine that our bounded sequence starts to look like this, and we're going to select a subsequence, which we will show as convergent. As we do that, and we start grabbing sequence terms to form a subsequence, remember this rule. A subsequence must be a sequence in its own right, so we will need to select infinitely many terms. And it must preserve the ordering that those terms appeared back in the original sequence. So for example, I could select A1, and then A6, and then A12, and then A13. But at this point, I could not go backwards to, say, A10 or A7, nor could I select A13 again. We must always move left to right in the sequence in a strict way. So a valid next choice would be something like A17, followed by A21, followed by, let's say, A25. So this is the heart of the proof, is we are just going to start selecting terms from the sequence in order to build up a subsequence. Here I'm building up the subsequence A1, A6, A12, A13, A17 I think was next, and then A21, A25, etc., etc. But we will be picking our terms in a very prescribed way in order to guarantee that they are getting pairwise close together, forming a Cauchy subsequence, which will then in turn converge. Okay, so let's get into the heart of the proof. The first thing we're going to do is recognize that since our starting sequence was bounded, we can literally bound it. So choose some real number b large enough so that the entire sequence can be squeezed between negative b and b on the number line. We are going to work with a family of intervals. This is our first interval going from negative b to b. Now that we've identified this interval, what we're going to do is pick a subsequence term. We have the entire sequence to choose from, so to make life easy, let's just pick the first term in the sequence to be the first term in the subsequence. You don't have to do that, but it's a nice choice. Okay, so with this interval, I'm going to do two things. I'm going to pick a subsequence term. I've just done that. It happens to be a sub 1 itself. And I'm going to recognize that the length or width of this interval is, in this case, 2b. So from negative b to b on the number line. Now what we're going to do is pass to a smaller interval on the number line. We'll call it I sub 2. And here's how we're going to do that. Let's split I sub 1 into two pieces. The left-hand side goes from negative b to 0, and the right-hand side goes from 0 to b, as I've done on the illustration. Together, these two halves form the original interval, which means that together they contain every single member of an infinite sequence. Therefore, at least one of these two halves must contain infinitely many sequence terms in its own right, because if both of them only corresponded to finitely many sequence terms when you glue them together, you wouldn't have an infinite sequence. With that information, the next interval that we will care about is whichever one contains infinitely many sequence terms. Perhaps both of them do, but in that case, you just make a choice. So choose I2, our second interval, to be a half of the original interval, which contains infinitely many sequence terms. And for the sake of this argument or the illustration, let's imagine that it's the left half. Okay, so we are going to now just focus on the sequence as it appears between negative b and 0. This is our new interval of consideration, and we are going to repeat the same two steps. I'm going to pick the next subsequence term, and I'm going to notice that the length of the new interval is b. It's half of what we started with. We need to make a little precision here. As I select the next term in the subsequence, I need to make sure its subscript is larger than the previous term's subscript, so that we are only moving strictly left to right with respect to our original sequence. So my note here about pick any n sub 2 greater than n sub 1 means make sure that you are selecting a later term from the original sequence. And you can do that because we are assuming that we have infinitely many sequence terms in this new interval. So since I sub 2 contains infinitely many terms from the original sequence, those subscripts go off to infinity. So you can pick a larger subscript. All right, now we're just going to keep going. So let's take I sub 2 and chop it in half. In the illustration, that's happening at negative b over 2. Once again, one of the two halves, or maybe both, must contain infinitely many terms from the sequence. Because if that wasn't the case, you'd arrive at a contradiction. When you glue them together, I sub 2 would only have finitely many terms from the sequence. Choose I sub 3 to be a half of I sub 2 that contains infinitely many sequence terms. In my illustration, I'm going to imagine that's going from negative b over 2 to 0. Then we need to pick the next member of our subsequence. Since infinitely many terms from the sequence appear in I sub 3, I can go out far enough to choose a term in the sequence beyond a sub n sub 2. So pick any n sub 3 greater than n sub 2, in other words, occurring later in the original sequence, so that it comes from I sub 3. And again, we can do that because there are infinitely many terms from the sequence in I sub 3. So we've made our next subsequence term choice, and let's also recognize before we leave this behind that the length of I sub 3 is half of the length that we were just working with. In particular, it's b over 2. All right, let's see if we can generalize this. Imagine we take I sub 3 and we chop it in half, as I've just done. That's happening at negative b over 4. And now imagine that it's the interval on the left side of this new chopping that contains infinitely many terms from the original sequence, so we can identify the next term in our subsequence there. I've just highlighted a random dot. We pick it in such a way that it comes later in the original sequence than a sub n sub 3. Then subdivide again. Pick another subsequence term so that we're really forming a proper subsequence. Subdivide again, etc., etc. So the general principle is that if you were just working with the interval named I sub k minus 1, you chop it in half and choose the next interval I sub k to be whichever half contains infinitely many terms from the original sequence. Then you pick the next member of your subsequence so that it belongs to I sub k, and it occurs later in the original sequence than the term you just selected. You can always do that because even though we are zooming in and chopping our domains in half and half and half, every time we do so, we still have infinitely many terms from the original sequence. So we can always look for a subscript that goes out far enough compared to whichever subscript we just selected. And I have here the pattern for the widths. It's a nice exercise to work that out, but you'll notice that the widths of the intervals as we've been zooming in satisfy this equation I have here. In particular, the width of the kth interval, I sub k, is 4 times that starting number b times 2 to the negative k. So when k equals 1, that was 4b divided by 2, giving us 2b. When k equals 2, it was 4b divided by 4, giving us b. And you see what happens is every time we're just going to cut that interval width in half. Okay, so this is the algorithm for how we build up this subsequence. We keep chopping it in half, zooming in, picking a new subsequence term so that we're building up a proper subsequence, chop in half, zoom in, pick a new term, etc. Now we've got our subsequence. We just have to prove that it really is Cauchy, and based on the picture, you can probably believe it's going to work out because our sequence terms are coming from a smaller and smaller interval. You know, if I keep cutting these in half, we're really, really zooming in on the number line. But let's formalize that. The first observation we can make is that the sequence of widths is 4b times 2 to the negative k. We have shown that if you have a base between negative 1 and 1, for example 1/2, and you exponentiate it to higher and higher powers, then you get numbers which approach 0. In other words, 2 to the negative k goes to 0 as k goes to infinity. Multiply that by 4b, you're still going to 0. So the widths of this family of intervals that we are creating, as we illustrated on the picture, shrinks to 0. Since the sequence of widths converges to 0 if we fix any positive choice of epsilon, we can then go choose an index capital K from the natural numbers, such that the length of the kth interval, I sub k, is less than epsilon. So given a choice of epsilon greater than 0, this is how we choose some threshold index capital K. Next, choose any pair of indices satisfying little m is greater than or equal to little j is greater than or equal to this threshold capital K. I haven't explicitly said this yet, but you probably noticed it. The way that we constructed our intervals, they are nested. Therefore, when we look at these subsequence terms corresponding to m and j, we can say that if a sub n sub m is in the mth interval I sub m, then it also belongs to the kth interval I sub k. And likewise, a sub n sub j, by belonging to the jth interval I sub j, also belongs to the larger enclosing interval I sub k. And that's because m and j are further out than k, so we've gotten to them through the subdividing process. So now if we take any pair of terms in our subsequence beyond this threshold and we try to compute the distance between them, what we can say is that the distance between them is less than or equal to the length of that kth subinterval because they both live inside of it. So the distance between them is less than or equal to L sub k, but by the way that we chose this threshold index capital K, that is less than epsilon. Therefore, the subsequence that we have created is Cauchy, and as we proved before, the set of real numbers is complete. Therefore, this Cauchy subsequence must converge to an actual limit, which is a real number, and therefore we have proven that our bounded sequence A sub n has a convergent subsequence. This second proof of the Bolzano-Weierstrass theorem is larger and more involved than the first proof that we did, which just used monotone subsequences and the MCT. So why did I bother to do this? Because I think it's a skill in real analysis in general to construct a subsequence kind of algorithmically as we did. So it is often the case, both in real analysis 1 and 2, that we will prove facts by taking some situation. Here the situation was that of having a bounded sequence, and we will construct a subsequence. And as we do that, we will provide instructions for how to select the next term. So this idea of, okay, given what we've just done, here's how you go find the next term in the subsequence that we need to create, is a skill to develop. So this is just a nice illustration of this idea of creating a subsequence in order to illustrate a certain behavior. I want to make one more remark before I stop this video, and that is that we built up a family of nested closed bounded intervals, so you may have been expecting me to use the nested interval property, and I actually could have done that. So in the next video, what we will do is just step back for a moment and look at the results that we've had so far. I will show you a chain of implications, the implications that we followed over the course of these videos, but I will also show you alternative routes through the material. Because as I've mentioned before, in a real analysis course, you can have different paths through the material in order to get to the same results, which are equally rigorous, but which order things differently. So I've ordered these results in a certain way, but I will show you other ways in the next video. Thank you for your attention.